Okay, great. Good morning, everybody. So welcome to this AIP special lecture today. So I'm Masashi Sugiyama. I'm chairing the session today. So it's my great pleasure and honor to introduce Professor Shai David as the speaker today. So I think I formally met him for the first time at NewRIPS 2006. So we organized a workshop on distributionship, and he was one of the invited speakers to the workshop. He really gave an excellent talk there, and his paper later on cited thousands of times. And that's amazing. I was so surprised and enjoyed his talk there. And since then, so as you know, he published a famous textbook on machine learning, understanding machine learning. So this is a kind of Bible textbook for almost all postdocs and students, even in Japan. So it's my really great pleasure to have him today. So he will be talking about learning probability distribution. Okay, Shai.
No, thank you very much, Masashi, for the nice introduction. Yeah, we really met many times in Tübingen, and so it's really great to be here, and thank you for the nice introduction. So what I want to talk today about is the learning of probability distributions. A general problem in machine learning, in statistical machine learning, is that we have some unknown probability distribution, some unknown phenomena, environment, and we get a sample that is drawn from this environment, and we want to learn as much as possible about the environment from the sample that we collected. So that's a very general setup. That's basically what is happening in statistical machine learning. And the first two questions to ask, you see, so this distribution could be a distribution of images with labels, or it could be a distribution of text, or a distribution of images without labels. And there are two questions that we just get a sample of this unknown distribution. It could be a distribution of patients. And there are two things we can ask. First of all is, what prior knowledge do we have about the distribution that generates the samples? We know that without any prior knowledge, there's no free lunch, we cannot do much. And the other question that we can ask is, what information about the distribution do we wish to deduce? Do we want to learn the labeling rule? Do we want to learn a clustering? Do we want to learn the average of the distribution, some other moments? So these are two aspects. What prior knowledge we start with, and what about the distribution do we wish to learn? So the most ambitious framework is that we assume no prior knowledge, and we want to learn what the distribution is. So this is density estimation. You have unknown distribution, it generates some samples. You want to know what is the distribution, generate some samples. Of course, I will not be able to know the distribution exactly, but could I approximately get a good approximation of the distribution, say in the total variance distance, in some distance between distributions. So this is kind of the situation. There is an unknown distribution. The unknown distribution generates some IID samples, and we want to conclude some D hat that will be approximately close in the L1 distance to the D, the generated distributions. So what I'm claiming is that this is very challenging. If we don't have any prior knowledge about distribution, and we want to learn what the distribution is, I'm claiming this is impossible. But let me, before stating it as a theorem, let me demonstrate what the problem is. So assume that we have a lottery. Every week, we throw 6 dice, and the ballot that guesses those 6 numbers wins the lottery. And now assume that I'm the lottery manager, and I want to cheat. I'm not happy with my salary. I want to get some more from the lottery. So what do? I toss the dice 1,000 times and record all the results. And then in the following weeks, instead of tossing fresh dice every week, I just randomly pick from the collection of 1,000 outcomes that I had drawn before. You see, for me, it's a big advantage, because all I have to do is buy 1,000 tickets and fill in all those 1,000 results that I have, and I'm sure to win the lottery. it's a big cheat. But the question is, assume that there is an observing referee that is trying to find out if the lottery is cheated or not. How long will it take the observer to notice that I'm cheating? Because I'm drawing from 1,000 results that were generated in the right way. How can they tell that I'm just drawing for a collection of these 1,000 results rather than from the collection of the many other possibilities? And if we think about this problem, when will an observer notice that I'm cheating? You realize that the first time they observe, if I'm drawing for my 1,000 examples or taking in some order, the first time someone will notice that there is a problem is when I first time take a same outcome twice. If the same outcome appears twice, you know that something is wrong. But as long as no outcome appears twice, how do you know that something is wrong? That's not the original distribution. But notice that those two distributions are extremely different. One is the distribution over all possible outcomes, and the other one is just distribution over a small set of 1,000 outcomes. So if
those 1,000 examples are also IID.
What? Yeah, it's IID. I'm drawing IID from these 1,000 examples. That's what I'm doing as a cheater. Instead of drawing IID from all the possible examples.
But why is it a cheating?
Because I can now win the lottery for sure. I buy 1,000 tickets and I have all those numbers recorded, and I just gamble on all these 1,000 tickets.
Sure.
And I'm sure to win every week. So it's a big cheat and you cannot detect it. I'm drawing IID for my 1,000, but instead of drawing IID from the whole distribution. Right. And we cannot detect it. So to turn it into a theorem, the claim is that samples of size which is independent of the domain cannot distinguish between two generating distributions that in total variance, they are half apart. They are really apart. So here is the proof. So, and what I'm doing here is just formalizing my previous example. So consider that you have a discrete finite domain set of size capital N. That's the set of all possible draws of the lottery. And now we know that if I draw a sample of size less than square root of N, it is unlikely to contain any repetitions. You know, that's the birthday paradox, that if you draw randomly at uniformly square root of N, that's when you start being likely to see repetitions. But if I draw less than square root of N, I'm not likely to see any repetitions. But if I don't see any repetitions, then it is equally likely that it was generated by a distribution which is uniform over all of the endpoints, or it was generated by say a subset of a half, which contains all the samples that I saw. You cannot tell what was the case. And these two distributions have distance a half between them. And the conclusion is that unless I see square root of the domain size, I will not be able to tell this difference between very different distributions. And of course, square root of the domain size is infeasible because many distributions are even over, you know, say real numbers that I describe them in 256 bits. So the domain size is 2 to the power 256. It's crazy. You'll never get even the square root of this. So my conclusion is that if we don't make assumption about a distribution and we want to know what a distribution is, we are likely to fail. So
could you draw a little bit of, because the term came suddenly for me, so I don't know sample of sizes and domain sizes in the previous example.
Okay. The domain size in the previous example is the whole possible set of lottery outcome. It's a very big domain, right? Now I'm drawing samples, and I drew only 1,000 of them. So I'm saying if I drew only 1,000, I will not be able to tell if I am uniform over this small subset, or I'm uniformly drawing from all of the domain. Okay, so the size of the sample here was 1,000. The size of the domain set was all the possible outcomes of the lottery. And
Sample generating distributions is the one that's generating the 1,000, and the one that's generating.
exactly. So one is the true, without cheating, uniform over all the outcome of the lottery. And the other distribution is the distribution of the cheater that just picks randomly from 1,000. And what I'm saying, if you're not in order of 1,000, because I was speaking from 1,000, or in general, half the set, you will not be able to tell that I'm not uniform over the distribution. Okay? So these are two very different distributions, but from a sample point of view, I cannot distinguish between them. So the conclusion is that without prior knowledge about the distribution, if I want to know the very ambitious task, what is the distribution, I cannot. Okay? So what I'm saying is that what follows is that we have two directions to proceed if we want to have guarantees of success. One is we assume that the generating distribution has some form. Say the generating distribution is restricted. It's a mixture of Gaussians. Say I'm assuming that the distribution is a mixture of k Gaussians in Rn. Then I have some knowledge about the family from which the distribution comes. That's what I call prior knowledge. The other direction is to say, I don't make any assumptions of distribution, but I ask the learner only to find out limited information, not the big question what the distribution is. So some information about the unknown distribution. Say I want to predict labels, I want to find the means, higher order moments. So if I just want to find the mean of a distribution, then we know that I can approximate it without any assumptions. Okay, so what I'm saying is that we have here two directions to go. One of them, make assumptions about the distribution, and then see under which assumptions we can learn the distribution. The other is say we don't make assumptions, we don't have prior knowledge, but we are modest. We just shoot for some answering a fixed set of questions, but not what is the distribution. Okay, and now I'm going to present results in both of those directions. So the direction of learning a distribution with prior knowledge, we have these results, the learning mixture of Gaussians. So in 2018, with Ashtiani, which was my student, and me, and Harvey, Liu, Merhabian, and Plan, we settled the sample complexity of this task. So we showed exactly how many samples you need in order to learn if you assume that the distribution is a mixture of Gaussians, which is a very important family of distributions. And we know exactly, I will show you later, we know exactly how many samples will suffice for reliable estimation. Another question about is, you see, so now we established that you can learn mixture of Gaussians, but you can ask which other families of distributions are learnable. What other prior data suffices to learn a distribution? And the question is, can we characterize which families are learnable? You see, in the very simple case of binary label prediction, if you ask me which families are learnable, I know what the answer is. It's the families that have finite Vapnik-Chervonenkis dimension. This is a fundamental theory of statistical learning. So we have a characterization of when classification with two labels will succeed. If your prior knowledge is a class of finite VC dimension. But the question is, do you have such a characterization of which families of distributions are learnable from just samples, unlabeled samples. So that question was posed more than 30 years ago and remained open until this year that with my student Tosca Lechner, we proved that there can be no dimension. That's a very strange result. We say that there's no hope to find a dimension that characterizes distribution learning the way that the VC dimension characterizes classification learning. So I will also talk a bit about this result. And we also showed that another interesting property of learning distributions, I don't know if you saw, there was a paper 2 years ago that says realizable is all you need. If you want to characterize learnability, if you can learn in the realizable case, then you can learn in the robust agnostic case. And they showed it for many tasks, and we showed that for distribution learning, this fails. Okay, so this is as far as restricting the family of distributions and asking which are learnable. Now to the other question, I can ask which properties I can learn about the distribution without prior assumptions. You remember we had these two directions to continue. Either I restrict the family of distribution with prior knowledge, or I don't have prior knowledge, but I just ask to learn certain properties. And we asked, which properties can you learn? And that is a result with Rubes, Moran, Spilke, and Yudayev. And we show that this is also a very strange situation. The answer to this question is independent of set theory. So just to give you the context, you know, there's the Gödel incompleteness theorem, and Gödel incompleteness theorem tells you that in every reasonable mathematical theory, there will be questions that you cannot decide whether the answer is yes or no. And we know it for the continuum hypothesis. We know it for all kinds of questions in set theory. But here we showed it for the first time for a question in machine learning. For the question, which properties of distributions can you learn without assumptions? The answer is mathematics will not be able to give an answer. It falls into Gödel's incompleteness theorem, which is very strange combination that was not expected. Okay, so I will try to describe these results. It's a lot of results and see how much I can cover. Are there any questions about the statements of these results? Yes.
So that's like if I find one property which is learnable, that doesn't
violate it, right? Right, we know, for example, if the property is learn the mean, then we can do it.
What is exactly independent?
The independent are two things. First of all, we show that there is a property such that being able to learn this property, you cannot tell if you can learn it or not. And we also show is that the question of, as a consequence, there can be no characterization of which properties are learnable. Okay? Yes. I don't hear you.
I mean, what will happen if some distribution, a family of distribution is not allowed? So to my understanding, so for distribution, we have a family of some thousand of natural base that is some specified mathematical formulation, and we have data on situation. It seems that such family of distribution is always learnable by it will be constant.
Okay, so I mean, you kind of phrase the question as a combination of two things. For a restricted family of distributions, we just show that you cannot have a dimension that will tell you what is learnable and what is not learnable. I gave you an example of something which is not learnable. If the family is the family of all distributions, we show that with the lottery example that you cannot learn it. So we know that you have to restrict the family. But the question is, on one hand, all distributions is learnable, not learnable. On the other hand, mixture of Gaussians is learnable. So we ask, where does the boundary go? Can we distinguish between those that like mixture of Gaussians unlearnable, or when do they become too big and you cannot learn them? That's the question that I'm asking. Okay. And that is not, that's something we prove, that you cannot define this boundary. Okay. Any other questions on the? Let me move on to talk a little bit about the concrete results. So what are the tools that we are using in the theory of machine learning? We have this notion of a class being pack learnable, which means you specify your accuracy epsilon, you specify your confidence delta, and then you get a sample size that tells you it's pack learnable. You have a number of examples you will need for epsilon delta learning. Then there is learnability with ERM. ERM, we all know what it is, and we know that in the binary classification case, if it's learnable, any ERM algorithm will learn it. Another tool is weak learnability. We know that if a class is learnable up to, say, epsilon equals a third, then you can use boosting and get arbitrary precise learning. And then we have uniform convergence. I will not mention more about it if you're not familiar with it. There is a notion of sample compression schemes that I will talk about in a second. And there is a combinatorial dimension. So in the case of binary classification, the combinatorial dimension in binary classification is the VC dimension. So all of those are different ways to attack the question of, is the class learnable? If you have a positive answer to one of them, you have a positive answer to all of them. So in the case of binary classification, the fundamental theorem of statistical learning say, given a class H, all the above are equivalent. And the relevant dimension is the Vapnik-Chovanekis dimension. And the equivalence is even quantitative. If I give you the VC dimension, you know how many samples will you need, not just that it's learnable. Okay, that's binary classification. And now, before I move on, we will see that this equivalence break down when we go to other tasks. But before I go on, you see, I had here existence, the one before last, is existence of sample compression schemes. And this will be a tool that I will use for my proofs in all the cases. So I want to explain a little bit what is this sample compression schemes. So what are sample compression schemes? Basically, it comes from the philosophy of the Occam razor. Occam razor tells you that if you have many explanations, you should prefer the shortest explanation. So one manifestation of this learning is the theory of sample compression for binary classification. It was introduced by Littlestone and Manfred Warmuth in the late 80s. And let me explain to you what is sample compression scheme. So a sample compression scheme goes like this. There is a class of models, say Gaussian distributions, or a family that you want to learn. And you can view it as a game between Alice and Bob. So Bob and Alice, both of them know what is the class of distributions. That's the prior knowledge. But Alice also knows which is the specific distribution that generates the data. Okay? And now Alice draws IID samples from D. And the question is, can she pass to Bob only a few of those samples such that he will be able to reconstruct all the relevant information? So what Alice does is she compresses the sample. Instead of sending to Bob the whole sample, she sends to Bob only a few points. And this is a good sample compression scheme if they have an agreement by which Bob can recover the knowledge that was in the sample. So just to give you a simple example, assume that we are trying to learn a half space in RD. And it's all the points on one side are positive, all the points on the other side are negative. Now you draw a sample. If you draw a sample, if I give you the boundary points, if I give you D points, some positive and negative that are defining the classifier, then you don't need all the rest of the sample. From those D many points, which are just closest to the boundary, you can now recover what is a good separating hyperplane, and you will be able to now give the correct labels for every point on the sample. So if I want to, if my class F is the class of all linear half spaces, then we know that we have sample compression. All I need is D plus 1 points, right? Or if I'm trying to learn boxes in Rn, you have a sample, there are plus inside the box, there are minus outside the box. You get a big sample. All you need to tell me is what are the top and bottom up positive points and leftmost and rightmost positive points, and I can draw the rectangle myself. Okay, so Littleson and Varmus introduced it in '86, and they showed that if you have sample compression scheme, then you can do learning. Then they show a compression scheme for binary classification, and it implies learning. And it was open for almost 30 years, whether every time that you are learnable, you can have a compression scheme. And Moran and Yehudayev, which are two of my co-authors of the last result, they showed in 2015 the reverse implication, that for binary classification, you are learnable if and only if there is such a compression scheme. If all your task is to classify plus or minus, binary classification, whenever it's learnable, there will be a compression scheme. Yes.
The information that Alice sends about the example that you gave in the compression scheme when Alice said it sends information to Bob. In the compression scheme, you said that this was an IID draw, but in the example of boxes, that wasn't a random choice.
No. I mean, the original sample that Alice had is IID. Now she picks from this original sample that was Anna's IID, she picks the 4 most informative points and sends them to Bob. So she starts with an IID sample, but now she knows what you want to convey, what she wants to convey, and she picks points which are most informative. So what Bob gets is not IID. Okay? Are there any questions about this idea? Okay, so we know for binary classification, you remember I had this equivalence of all possible tools, and this is just saying the tool of compression scheme is equivalent to learnability. So more generally, what we showed in the 2018 is that if you have any family and you have a compression scheme to size T, then you can learn up to precision epsilon with only T over epsilon square examples, roughly up to polylog factors. So if you have small compression scheme, then you can have efficient learning algorithms, not only for binary classification, but also for distributions and for many other types of tasks. Why is that the case? Because, you see, let us just pause, see what the problem we're trying to solve. We know that Alice can send Bob only a few points. Now the question is, how many points do I need in order to learn? There is no Alice that will send me the informative points. I'm just Bob. I just see an unlabeled random sample. How do I learn? So what I can do as Bob, I can say, let me try to simulate Alice. What could she have sent me? She could have sent me this small number of points, or that small. What is happening here? Okay, it's running without me, but my getting impatient. So what could I do as Bob? I could try to simulate Alice. I could look at all possible messages that Alice could have sent me. How many such messages are? If the sample size is size M, and I know that there's compression to size D, there are only M to the D possible messages that Alice could have sent me. So with each of those m to the d possible messages, I say, oh, if I got this message, this is the assumption that I will go with. So now I'm left with just m to the d many assumptions. So instead of, say, trying to learn arbitrary mixture of Gaussians, now I only have m to the d many Gaussians to pick between them. And then we can pick between them with precision epsilon with taking d over epsilon square examples. So you see, if we have a small compression, I can take your big family of coming from your prior knowledge, and by simulating Alice, I can reduce it to a finite family. And now it's just a question of how many samples do you need to learn from a very strong prior distribution. It's one of those m to the d many models. So that's the basic idea, how sample compression implies learnability. So now I want to show you how did we get, with this idea, we got sample compression for mixture of Gaussians, and that gave us the result on how to learn mixture of Gaussians.
What is m to the d?
Again. Okay, m is the original sample size that you had. D is the size of the compression. So you know that Alice would pick D points, but you don't know which. So how many possibilities you have to pick D points? M to the D many possibilities. So for each of those possibilities, you recover, if that is what she sent you, what will be my model? And now I have a small collection of models, okay? So how do I compress mixture of Gaussians? Which is, so it seems, let's start with the simplest case. I have one Gaussian in R1, in one dimension. How, you give me a sample. I'm Alice. How can I pick 2 points to send to Bob? So what I'm saying is, if I see enough points, then I can find, here is the sample that Alice got. And do I have, yeah. So say Alice could pick 2 points, those red points, such that the average of these 2 points is roughly the mean of the distribution. And the distance between these 2 points is roughly the variance. So what we see here is that if we want to learn one Gaussian in dimension 1, Alice can compress to 2 points. Once Alice sees a big enough sample, she picks 2 points that tell you what is the mean and what is the variance. Okay, so now what happens if instead of one Gaussian, I have a mixture of Gaussians? So if I have a mixture of Gaussians, here is my mixture of Gaussians, the different colors. So now Alice gets a sample from this mixture, and now she will pick 2 representatives from each component. Alice knows what is the generating distribution, so she can pick 2 from each component. So we know that if I have a collection of k Gaussians in R1, I can manage with 2k points compression. Okay, and then we know that if I have compression size t for learning one Gaussian, then I will have compression size kt to learn a mixture of k Gaussians. I'll just pick the compression of each of them, and that will be my message. So I skipped one point here just because I'm trying to squeeze lots of results into this talk. How do we go to RD? So if in D dimension, it turns out that I can manage, that Alice can manage, maybe D is not a good name here because I use D for the compression chance. If we dimension n, Alice can manage with n square points. For every, you look at the covariance matrix, and for every axis, you pick 2 points that tell you what is the mean and the variance along this direction. So if we are in dimension D, you can manage with 2D points for one Gaussian and k times 2D for a mixture of k Gaussians. So now we proved our results, because we know that if you can have compression of size kd square, then the sample size that you need to learn is KD squared over epsilon squared. Yes.
Just clarification on the previous slide. Do you not need to somehow compress like which points belong to which Gaussian?
Right. Very good. Very nice. So the point that he noticed was that I also need to tell Bob which points came from which Gaussian. But that I could give you, that's why, you know, I have this tilde over the O here in the bound. This I can tell you with very few bits. I can just decide that I'm sending you them in order. The first belong to the first Gaussian, then the second, and so on. So all I need to do is give you the index of every point, which will take me log of the number of points that I'm sending. So that's true. I need this extra information. But the extra information will not disrupt this idea that Bob can recover all the possible messages from Alice and get this finite set of candidates.
So in terms of connection between compression and learnability, so the compression doesn't necessarily just
Right.
be made out of points.
Exactly. The compression can be made up of points plus a binary vector of hints. As long as this binary vector of hints is short, everything goes through. Very nice. Yeah. Yeah. Are there any other questions here? So you see what the way we cracked here a problem that was open for a long time. This got best paper award in NIPS, and it looks like the proof is very, very simple. But the insight was that we are using compression. And when we use compression, we have this modularity. If you can compress one distribution to D points, you can compress a mixture to KD. If you can compress in one dimension, then you can compress in n dimensions by just the square of the number of points that you needed, and so on. So that the insight here was, the novelty was the use of compression schemes for showing the learning results. So this improves all previous known bounds, and there are really tens of papers that were shooting for learning mixture of Gaussians, and it's nearly tight. We also show the lower bound that is matching up to logarithmic factors. And we even showed it for agnostic. So what does it mean, agnostic? The assumption that your distribution was a mixture of Gaussians is very strong. Instead, you want to say, my assumption was from something which is close maybe to it, can be approximated by a mixture of Gaussians. And then if your generating distribution can be approximated by a mixture of Gaussians, we can still approximate it with the same sample size. So this is a case where the agnostic case, in which we don't assume that it's exactly a mixture, and the realizable case in which we assume it's a mixture can be solved with the same tool. I already mentioned that in the general case, we separate the two models. Okay, so that's as far as I wanted to discuss this first positive result. And I want to switch now to some negative results. I mean, if Masashi knows me, knows that I'm much more often publishing negative results than positive results. So let's go to some negative results. Okay, so what do we have now? We established that a mixture of Gaussians is learnable, and there are two following obvious questions. First of all, can we learn the mixture of Gaussians efficiently? Because all I showed you is sample size, but I didn't tell you how much computing time you will need. Can we do it in polynomial time in the dimension and the number of Gaussians? And this is still open. So in many cases in machine learning, the sample complexity is much easier to solve than the computational complexity. And here it's still open. The other questions is, as I mentioned before, which other families of distributions are learnable? Can we characterize which families are learnable and which families are not? So here, what do I mean by characterization of learnability? So here is a long list, and it's not even includes everything, that if you want to do batch binary classification, we know that you are learnable if and only if your class has finite Vapnik-Chevolaitis dimension. If you want to do online learning, then we know that mistake-bound online learning, it's characterized by something which is called the Littlestone dimension. There is a dimension that characterizes it both in the realizable agnostic case. If you want to do real-valued functions, we have the fat shattering dimension. It's an old paper of myself with Nicholas Zabianchi and David Hausler and Manfred Warmuth. If you want to do multi-class learning, there were upper and lower boundaries dimensions, and recently Danieli and Shalev Schwartz got a precise dimension. If you want to do robust learning, there is the dimension. So what I'm saying is for many, many learning problems, we have a combinatorial dimension that tells you when is the task learnable and when it is not. However, there are few cases for which we don't have a dimension. So this is learning probability distributions, as I mentioned, we don't have a dimension. Another one is classification with respect to a restricted family of distributions. That's another interesting question. When I do binary classification, the VC dimension tells me if you have finite VC dimension, then no matter what the marginal is, you will be able to learn it. But in reality, the distributions are not as bad as possibly be. So you can say, if I assume that my set of marginals is nice, say they are all smooth, they are all Lipschitz, they are all, can I learn more than without any assumptions? So I want to classify under which assumptions on the niceness of data will I be able to learn. The VC dimension, if VC dimension is finite, you can learn everywhere. But it's really a realistic question. What can we guarantee if we know something about the niceness of the generating data? And another question is learning real valued functions. So for all of these, there is no known dimension. So we have a long list of tasks for which there is a dimension characterizing learnability. For these tasks, there is none. And for those are questions that has been around for, we have record of people asking questions about it already in 93 and 94, 30 years ago. So as a result, with my student Oskar Lechner, we showed recently, this is under submission now, that there can be no dimension for any of those tasks, which is a big surprise because this comes at the top of a long sequence of papers that show dimensions for all kinds of things, even for private learning, for robust learning, very recent papers, taking different tasks and showing here is a dimension that tells you when you're learnable and when it's not. And these cases remained open, and we showed there can be no dimension for all three cases that I mentioned above. Okay, so to move on, I mean, I think the obvious question, I don't know if you are still having patience with me, but if you do, the obvious question is, how can you show, in order to show that no dimension exists, I need to define what I mean by dimension. I mean, so the next step, I want to devote a little bit of time to this question of what do we mean by characterizing learnability by a dimension? Because without defining that, how can I show that no dimension exists if I don't know what dimension is? So we need a clear definition of what a characterization is, and we consider two types of characterization. One is quantitative, like the VC dimension, that if you know the VC dimension tells you not only that the class is learnable, it also tells you how many samples you will need, right? If you tell me epsilon and delta, your precision requirements, the VC dimension tells you how many samples you will need, roughly the VC dimension over epsilon squared. So this is what we call a quantitative notion or dimension. And there is a qualitative one that will just tell you learnable or not learnable. So we will give a different definition for what does it mean to have a quantitative dimension versus just a qualitative dimension. So here is the first definition. What should be a quantitative dimension? So a quantitative dimension, it's a function D that goes from the family of all classes to either a number or infinity. And you want that a class is learnable if and only if the dimension is finite. And you want that if you want to know what is the sample size, so let us look just as this last line. If I want to know what is the sample size, MQ of epsilon delta is how many samples do I need in order to learn the family Q with precision epsilon delta. I want it to be a function of just the dimension on Q and epsilon and delta. So I want that the dimension will tell me all there is to know in order to figure out how many samples I need. Once I know the dimension, I can tell you how many samples you need. I don't need more details about the distribution, right? So what I'm saying is all the information about the class that you need in order to determine the sample size is captured in D of Q. The sample size is a function of D of Q and epsilon and delta. You don't need more about Q. That's the notion of a quantitative dimension. Once you know the dimension, you know the quantity of samples you will need. That's a strong notion of dimension, but all the dimensions that I listed for all the other examples, they are quantitative. There's a question here? Or? Okay, now what is a qualitative dimension? A qualitative dimension is a sequence of properties. So we have a countable set of properties W such that the class is not learnable if and only if it satisfies all of those properties. So before you go to the second point, just what do I mean here? Say the properties are saying you are harder than D. You are harder than D plus 1. You are more difficult than D plus 2. If you satisfy all of them, it will be impossible to learn. It's like saying the VC dimension is D, which means you're pretty hard, but if it's not D plus 1, we know you can learn. But if I shatter D points, I shatter D plus 1 points, if you're familiar with the VC dimension. The more points that you shatter, the harder it is to learn. So those properties are, can you shatter D points? Can you shatter D plus 1 points, and so on. So if you satisfy all of them, you are not learnable. And if you don't satisfy from a certain point on, you are learnable. And the second requirement is that each of those properties can be demonstrated by a small set, by a finite set. You see, if I tell you that you shatter D points, then in order to demonstrate it, you just need those D points and the 2 to the D many functions that shatter them. So there is a finite evidence that you are hard. So this W is a set of hardness requirements, and we want that each hardness requirement can be demonstrated by a finite core. If you contain this finite core, then you are so hard. This is our notion of quantitative dimension. And again, all the dimensions have these properties. All of those dimensions, VC dimension, Littleton dimension, whatever I mentioned, they're all both quantitative and qualitative. And also all the notions that people conjecture. There was a conjecture of what should be the dimension that characterizes learning distribution. If you look at the Lugosi-Devroy books on learning distributions, there is this conjecture. It also satisfies those requirements. So what we showed, do I have a slide? Yes, that no such dimension exists. There can be no dimension of any of these types for any of those 3 problems for which we didn't know if there is a dimension or not. And that's also a very unexpected result. Okay, so I will not, due to time, I will not get into the proof here. I'm very happy to discuss proofs with anybody, but these are combinatorial proofs here. We just construct families of distributions that refute all of those possible notions of dimension. Okay. So I want to use whatever time I left to look at the other problem. You remember, I said there are two directions in which we can do guaranteed results in learning distributions. One of them is restricting the family of distributions, like mixture of Gaussians. The other one is what properties of distribution do you want to learn? So now I want to talk about the second part, learning to answer queries. So which questions about an unknown probability distribution can you answer reliably from an IID sample without any assumptions about the unknown probability? Okay, so a general learning tool, if I have a family H of real valued functions, of questions, of queries, uniform distribution is the following, says you get an IID sample and you want to estimate the expectation of which of the answer to the questions. So I have a collection of queries. What is the mean? What is the variance? What is the second moment, third moment, and so on? And I say, you get a sample, can you estimate reliably all of them? This is called uniform convergence, and we understand it very well. Uniform convergence is kind of equivalent to VC dimension. But in many cases, we don't need uniform convergence. So what do I mean by that? So in many cases, all you need is, you don't need to estimate all of the models. You only want to find the one that is roughly the best. So think of a problem, say, I want to do k-means learning. I have an unknown distribution. I want to know where is the best k points to put as centers, so I will optimize the k-means loss over this distribution. So that's a kind of a query like this, right? I have an unknown distribution. I see a sample. I want to find k points that will minimize the k-means distance, the k-means loss, okay? So what I'm saying, uniform convergence will tell me if you get so many samples, for every k of points, you will be able to tell what will be the loss with respect to these centers. That's uniform convergence. No matter which k of points pick, if you add enough samples, you can tell how bad it is, what's the loss. But what we really care about is just find me k points that roughly optimize the loss. I don't need to know what is the loss of every possible k tuple. I just want you to find me something that has as good as possible loss, that minimizes the loss. So we call it the Emacs problem. The Emacs problem is, say, you are given IID sample, you have a set of queries, you want to know, give me the one that has close to optimal expectation. Does it make sense? And it turns out that many learning problems can be viewed as Emacs problem. For example, binary classification, you can say in the uniform convergence tells you for every hypothesis H, what will be the loss of H. But all I need is to find H that has the close to optimal loss. I don't need to estimate the loss of every H. So it's the same with multi-class prediction, with k-center clustering problems, as I just mentioned, with linear regression. Again, linear regression, you have an unknown distribution. You want to find a linear regression. You don't care that you will be able to estimate the regression loss of every possible linear function. All you want is to find a linear function that roughly optimizes the loss. So we call it Emacs learning, which is different than uniform convergence. And there are many other problems that fall under this Emacs learning. It turns out that we did not invent it. we reinvented something that already Vapnik in the 70s called the general statistical learning problem. This find me the model that maximizes the outcome. Okay, so let us focus on a specific case. Assume that all my queries is a collection of sets, and you want to know which set has the highest probability. Oh, think of it this way. I mean, I have a collection of products, potential products, and rather than estimating how many will be sold for any product, I want you to give me the product that is most likely to be sold. That in the distribution of my buyers, this will be the product that will interest them mostly. Or I have a collection of possible, say I'm university, I have students applying, they're coming from different countries. I want to say, tell me which country is most likely to send students to my university. So this is a specific case of the Emacs problem. You have a collection of sets, you unknown distribution, you want to know which set is the most likely to be visited by this distribution. So that's a particular Emacs problem. So for the class of all subsets of a domain, let's assume that my collection is all subsets of the domain. So you give me a sample, and I want to tell you which set of the domain is the most likely to be hit. You cannot answer it with uniform convergence, because if it's infinite, it has infinite visitor dimension. But can you tell me which set is most likely to be hit? You have all subsets of a domain X. You have an unknown distribution, and I ask you, give me a set that has the highest probability of being hit. What will you give me? You have all possible subsets. Can you pick the subset that will get the highest probability of being hit? What? Yeah, the whole domain. I mean, it's not. I'm not asking you for distribution. I'm asking for a subset, right? So if you have the yes. No, it's the whole set. If you take the whole domain, of course it will be hit with probability 1. Right? If your task was all possible subsets, among all possible subsets, which is most likely? The whole domain. That's trivial, but it shows you that maximization is much easier than uniform convergence. Uniform convergence will ask you, find me the probability of each set. It's impossible. But maximization is much easier sometimes. So we ask, can you characterize when is maximization possible? What I want to show you is, okay, it's trivial if you have all sets, but it becomes interesting if the collection of sets is limited. So we want to ask which classes of subsets are Emacs learnable. For which classes can you guarantee that you will find me the set that is almost most likely to be hit? Can we have a combinatorial characterization? And we attack it with compression. We ask, is there a sample compression? What do I mean by sample compression? So go back to Alice and Bob. So we have a collection of sets, and Alice and Bob play the game as before. Alice gets a sample from my distribution. So she gets a finite set S, and she wants to send to Bob a subset S prime, which is small. And what I want Bob to be able to do is I want Bob to find an output, to output a set that is a finite subset such that it contains all of the points that Alice saw. So think of it again. I mean, it needs a bit of a, you see, Alice got a collection of points, which was drawn by the distribution. She sends to Bob only a few of them. Bob wants to recover a set. Bob wants to guess what is a set that is going to be hit. can Bob recover a set that includes all the points that Alice showed him? Alice didn't show him. All the points that Alice gets. So Alice has a set of points. She wants to send only a few so that Bob will be able to recover a superset of what Alice had. That's kind of the game of compression that we want to play. And we ask, when is this doable? So can Alice send to Bob a bounded side sets? So it depends on the size of X. If X is finite, it's trivial. If X is finite and you have all finite subsets, collection of all finite subsets, Bob can, so the game we are playing now is just with finite subsets. We have all finite subsets of the domain. Alice gets a sample. Bob needs to recover a superset. So if it's a finite, it can give you all of X. But Bob is bound to give you a finite set. If it's countable, then also think of the natural numbers. If Alice gets a collection of natural numbers, can she send to Bob only one number so that he will be able to recover a superset of everything that Alice got? Alice got, so it's a simple game. Alice got a finite collection of numbers, 7, 8, 100, 2 million. Now she wants to send to Bob just one number, and he will be able to recover a subset that encompasses everything that Alice saw. What will she send Bob? The biggest number, right? It's very easy. If it's countable, it is compressible to one number. Okay, that's easy. Now try to play this game not on the natural numbers, but on the real numbers. So Alice gets a collection, a finite set of real numbers. She wants to send just a few points to Bob. He must return a finite set of reals that will capture everything that Alice said. Can you do it? This is now very challenging, right? If it was natural numbers, we knew the maximum. But if it's just collection of points in the unit interval, can she send him just a few points? And that's where we got our strange results.
Then you could still just do an interval.
What? But he has to send back a finite set of points.
You could send an interval.
The interval is not finite, it's infinite.
But
No, I'm saying my collection of sets, the game is you only have finite subsets. Alice got a finite subset. Bob needs to send back a finite subset that will include the set of Alice.
Then you can discretize.
So, and you discretize, and then what you just said.
Send the discrete.
But it's not the point, it doesn't contain the points that Alice had.
Well, you get an idea of where it lies.
You get an idea, but the game is you want to get them. You see, in the case of natural numbers, you do get a finite set, the initial segment. Everything which is less than 2 million, it's finite set. With real numbers, it's very difficult. Now, here is the strange thing. We showed that this is equivalent to the continuum hypothesis. Okay, so now it's a different story. What is the continuum hypothesis? I don't think I have it here on my slide. Cantor's theorem tells you that the real numbers is a larger infinity than the natural numbers, right? The natural numbers are countable. The real numbers is the continuum, it's uncountable. That's Cantor's theorem. But then the question was, how big is the continuum? Is it the next infinity above countable, or it's the next to next, or is it higher, and so on? And that's the continuum hypothesis. And we know that the answering this question is impossible. That was the first result of showing Gödel's impossibility principle, the undecidability of the continuum hypothesis. What we showed here is that Alice and Bob can play this game with D points if and only if the continuum is of size Aleph D. It's the D's infinite number. See, if the it is kind of hard to grasp. But the question is the real numbers. How high are they in the hierarchy of infinities? And it turns out that where they are in the hierarchy of infinities is the size of compression set that Alice can send. I mean, if it's in the bottom of the infinities, it's countable. We know she can send just 1 point. But if the continuum is the next cardinal, then she can settle with 2 points, which is very strange, but she can. But now the continuum can be Aleph 1, Aleph 2, Aleph 3, Aleph D, but it can be bigger than all of those. In those cases, there will be no compression. Now, let's take a step back. We said that learning is equivalent to compression. We showed it for this case. Compression here depends on how big is the continuum. How big is the continuum is independent of set theory. We cannot answer this question. Therefore, we cannot answer the question of what is learnable and what is not. In this setup of, I give you a collection of subsets, give me one that is most likely to be hit. So that's the impossibility result that we got, undecidability result. Okay, let me just skip to the conclusions. Okay, so that's, okay, and we also show that from this, it follows that you cannot have a dimension that characterizes what sets of queries are learnable and what's not, because if you had a dimension, it will not be independent of set theory. So, okay. So where is the independence coming from? The independence is coming from the fact that in usual learning theory, we assume that you have a function that takes training data and outputs a hypothesis. But somehow we didn't require that this function is computable, that you have a program for this. And if we had such a requirement, then there will be no independence. So following this work, we started to ask, what happens if you require that the learner is a computable function, is a program? The VC theory does not require it. And we could show that if we require computability, then the characterization, even of simple binary learning with VC dimension, breaks down. You cannot learn, there are classes of VC dimension 2 that you cannot learn them with any computable function. They are learnable because of Vapnik-Chervonenkis theorem, but the function that learns them, the ERM function, is not computable. And then we showed it for online learning. So it really opened a whole direction of saying, what if we add the requirement that our learner must be computable? What is more natural than this? What's the point of learning if I cannot write a program for it? But it turns out that if I add this requirement, then the foundations of machine learning theory break down with this requirement. Okay, so I guess I had enough confusions here, so I will stop here.
Okay, thank you very much. Any question?
A great talk today. So I have a stupid question. So why do we always characterize the learnability by dimension, by a real number instead of some object with properties?
No, it doesn't necessarily have to be a real number. So when I could go back to our definition of dimension, it doesn't necessarily have to be a real number, but you want to extract some kind of concise information about the class, such that with this concise information, you will know if it's learnable or not. And you want this concise information to be testable. Of course, the concise information could be, this is learnable, but you cannot test it. But if I tell you the VC dimension is 100, you can tell me, okay, show me. give me 100 points and how they're shattered. So you want some kind of an evidence, concise evidence to learnability.
I see. So the most conceiving conciseness is real number.
What?
So can I say real number is is a form of conciseness?
Real number is, yeah, not very concise. The natural number is concise. When you,
Thank you so much.
right.
Yeah.
Thanks so much for your talk. So in the first part, learning mixtures of Gaussians, do you also handle the agnostic case that you mentioned later, where let's say, yeah, you don't necessarily assume the distribution is a mixture of Gaussians, but mixture of Gaussians is rich enough to handle lots of different probability distributions to approximate them up to, let's say, very good accuracy. So then, but then I guess, yeah, so this approximable class is very rich, but I mean, still not the same as all of distributions, right? Then you would need maybe infinitely many mixtures, but I guess it's an interesting problem that's
now we solved it.
very rich, right?
Yeah, it's contained in that paper. We showed how to learn in the agnostic case. So if the distance between the generating distribution and the best mixture that approximates it is, say, alpha, then you can learn up to distance 3 alpha. So we do have this kind of agnostic learnability with exact same sample size.
Okay, thank you.
I also want to ask that question for that. So some people try to distinguish like mixture of Gaussian model from other regular statistical model because the parameter and function is not one-to-one mapping in the case of Gaussian. Does it property like make any sense in the proof? Right.
So as I showed, I mean, the proof relies on the ability to compress. So Gaussians are very easy to compress. So now if you have another family, another parameterized family distribution, the question is, can you, if you have a single simplest example from this family and you get a sample, can you compress it to a few points? And whenever you can compress, the results go through. And then now you can just check every parameterized version that you like and see if you can get this kind of compression property.
I see.
The nice thing about Gaussians, they could compress a simple Gaussians in R1. All you need is to compress a simple distribution over 1 dimension. Then the machinery will kick in. It can go now for a mixture, it can go to high dimension. All you need is to, but for one Gaussian in 1 dimension, it's very easy to compress. If I have enough points, I have 2 of them such that their average is roughly the mean and their distance is roughly the variance. So the question, do you have this kind of compression for your other family?
Any other questions? Then, so it's almost time and maybe we should finish the seminar. So thank you very much.
Thank you.